So they give you fx is 3x minus 3. If you set that equal to 0, you get x is 1. Fy is y minus 2. Set that equal to 0, you get y equals 2. So that's where they got, of course, the point 1, 2. So unfortunately, they all say 1, 2, so you can't eliminate anybody off of that. But to check these, to check this point, use this guy. So if fx, that was fxx. 3. What's fyy? 1. And what's fxy? 0. Or fyx. And of course, these two are equal for this case, because f is a nice differentiable continuous function. We're assuming that anyway. Its derivatives are, so it probably is itself. Where are we at? Okay, so this is pretty straightforward then. If I plug it in, I get 3 times 1 minus 0, so I get 3, which is greater than 0. So if d is greater than 0, it's not a saddle point, right? To be a saddle point, d's got to be less than 0. What do I look at then to determine if it's a max or a min? I know it's one of those two things. Yeah, fxx. Fxx here is greater than 0, then this has to be a minimum. I like it. So 4b. Cool. Number 5, same idea. So what do you guys get for number 5? A? Anybody else got anything different? B? B? So 5 should be A. And 5, same idea. This one's a little bit more involved, but they kind of gave you the answer already. So you know the critical point is 0, 0. That's what they're talking about. Of course, 0, 0 certainly works there. I don't even care if there's other critical points for this problem, because that's the only one they're asking me about. So then you figure out what fxx is, you figure out what fyy is, you figure out what fxy is, you plug in that point, throw it into your d formula, and see how it comes out. That's the process. And like I told you, last semester I'm going to do the same thing this semester. I'm going to put on the test in a box the formula and how to interpret it. That's just way too nice. Yes. So that's not too bad. So this should come out to be A. Should be a saddle point. So how do you tell if it's a saddle point? And D has to be less than 0. So it's a saddle. Oh yeah, number 6. This one's kind of silly. So this is the function, and they tell you that my constraint is, or the region I'm curious about is inside that circle. Well, the largest x squared plus y squared, and thus the largest that f can be, is 5. So there's no, now if you want to double check it using the calculus, we could, right? We go through the same process here. We do fx is 2x, fy is 2y. We'll get 0, 0. Right? Now where's this going to kind of throw me off? 0, 0 is going to be the location of what? The minimum. And again, you don't even have to use calculus to figure that out. So the first step of this problem would be find the critical point that's in here. Right? These are the points that I'm allowed to use for this thing, right? That's what that tells me. It's kind of like my domain for this problem. So in here is 0, 0. That does exist in this region. So that's the location of something. So you throw it into the D formula and find out eventually this is a minimum. And we can tell because you're just going to throw it in that 0, 0 plus 3 is definitely small compared to what's the largest that the boundary gets. Like you told me, the largest the boundary gets is 5. And that would be f equal to 8. So number 6, the largest he gets is 8. And the smallest it gets is at 0, 0, which is 3. Cool. is actually 6 and 7. So 6, the biggest it gets is 8 on the boundary. Oh, I'm sorry.
See, I don't have the paper.
Gotcha. So 6 is C. And 7, the smallest it gets, the absolute minimum is 3. That's A. The one I thought might give us some trouble would be 8 and 9, possibly. What about 8? Okay, so I got one suggestion is C.
Yeah, C.
Let's take this problem and put it into 2D. What shape, of course, is a plane represented by in 2D? A line. You with me? Because if I just extend that line, if I just copy it, I get a plane. Right? So to get an equivalent problem in 2 dimensions, I draw a freaking line. So if I have a line that has these endpoints, so it's defined, oh, let me make it more like this problem. From -2 to 2. You with me? So this is truly a 2D image. Cool? In this problem, this is 2D. In number 8, yeah. Number 8, the domain. The domain is the square. I love it. Which looks more like a rectangle up here, but oh well, too bad for us. I really don't know if you guys catch this, because a lot of people make mistakes. They look at this picture of a domain and they start treating it like it's the whole function. That can happen sometimes in this class. It gets a little confusing. In 3 dimensions, or well, in 3 dimensions, our inputs are in the xy plane. Right? They're points. In 2D, they're just positions on the x-axis. That's my inputs. So if I have a line that's bounded, where could the max or min occur? The absolute max or min?
On the boundary.
It could only occur on the boundaries. So that same idea is here. If I have a plane and I bound it off, it can't be inside because if I go a little bit in that direction or that direction, it's going to go higher or lower. Do you guys get that idea? I don't have to apply too much math here. This is a very conceptual question, just like this line. The most extreme case of a line would be one that's flat. But in that case, you could just argue that the absolute max and min, it's a tie all the way across the damn thing. So isn't it still at the freaking boundary points? Okay. You guys kind of with me on this? So no math really to do there. This is a very conceptual problem. But just the idea, if I have a region in my xy plane that I'm only allowing, it can't be inside because the minute I go in some certain direction, I'm going to go up or down. So it can't be a max or a min inside. It's got to be on the boundary point somewhere. Maybe. Okay.
For this case, the second derivative gives us 0, right? Because
Number 8, yes.
so
It's not concave.
So we have this function here.
It's flat.
yeah, I mean, it's still.
Yeah, so it's got no concavity. It never changes its slope. It's great. It's a directional derivative. It never changes. If I'm going in a certain direction, it doesn't change. It's a constant slope, right? So of course the second derivative is going to be 0. So what case am I in this case then? If I have this z equals, where am I at? Oh, there. 2x plus 3y minus 1. Cool? So then fx is 2, fy 3, fxy 0. So then 2 and 3, plug it in there. Well, actually, what does this lead to, actually? Is x equal to something here?
No.
These are constants, right? So at all points on this plane. So what's fxx? And I think this is your point. What's fxx?
0.
0. What's fyy?
0.
And what's fxy? 0. So D is inconclusive. Does that mean something? If it meant something, it wouldn't be inconclusive. It just says you can't say. You don't know. It could be anything. So in this particular case, it's actually too easy of a problem just step back and go, I don't need any of this shit. That's why this came out inconclusive, is because it's got no concavity, so the concavity can't help me out. So it's inconclusive because of that. Yep.
Could you also limit where you would find the boundary points by saying it's either a side of that square or a corner? It can't be in between a corner.
Yeah, that would be sort of the same idea as it can't be an interior. It almost can't be here either, because if you go in one direction or the other, it's got to possibly go up or down, unless it's that whole line is on there, and then that whole side would be the location of the absolute maximum. I really hope you guys can get that idea. That's, I'm sure I have a better way to do this. If I had a section in the XY plane, it can't be inside because there's a higher point. If I just go in one direction or the other, go higher or lower for this plane. The most extreme case would be this, where it's flat. This is not a what? It's a plane, but it's not a what? Function. It's not a function, so that wouldn't even be a part of this question. Cool. Okay. So number 8 is B. So you would find the absolute maximum value on a boundary point. It couldn't possibly be the interior, because if you go in one direction or the other, you've got to go up or down. It's a plane. You've got to go up or down from that, or stay flat in the extreme. Number 9. What's up with number 9? And can you see this on the first step? This is the kind of equation, I think this is not that terrible, but whenever you see square roots with stuff in it, you kind of cringe, do you? Is this true? I mean, I knew I did as a student. I still sort of do as a teacher. Okay, 3. But they're not that bad. You just got to keep track of which one's constant, which one's not. So in this case, of course, the y is a constant. The derivative of something to the, I mean, not derivative. Yeah, derivative of something to the 1/2 power is, well, it's that thing to the negative 1/2. There's a 1/2, and then of course, the inside gets his turn, right? It's not fair if I don't do the inside too.
2x.
2x, cool, because the y squared is constant. And when is that equal to 0?
Oh, 0.
Whenever x is 0.
If x is 0, or
When x is equal to y.
careful.
Imaginary number.
If x equals y equals 0, to be more inclusive, right? It equals 0 when x is 0. It's undefined when x and y are both 0. It's with me? Sweet.
Yes, that doesn't count there. If x and y is equal to 0, then it's not defined.
No, we're fine there. We're fine. That is perfectly good. Why? Because the original function has this in its domain, doesn't it? The only time we'd have to throw this out is if the original function didn't exist there, but it does. And I don't know if that's the way you were thinking about that, but that's a perfectly good point. Because the original function is okay with it.
Okay.
Fy, you get the same thing, just with a 2y over there, right? So you get, again, you get y equals 0, or x equals y equals 0. But what's wrong with saying fx 0, 0 equals fy 0, 0? What is fx of 0, 0? What is fx evaluated at 0, 0? Even worse than undefined. It's
Indeterminate?
It's indeterminate in a way. It's not really a limit, but it's still 0 over 0, which is officially indeterminate, so I can't really use that. That doesn't equal 0. Doesn't equal 0 factorial either, but I just want an exclamation mark. You guys with me? So that's not true, so I can eliminate part B. What's got to be true, though, because I got this?
Critical point?
It's got to be a critical point. So right there, I knew that must be the answer. It's a critical point. Some people look at that problem and they see 9a and 9b as saying the same thing, but you forgot that it deals with where it's undefined also. So one does not mean the other.
So it's A?
So 9 is A. Cool. What about number 10?
Those are actual values. values, like if f of x goes, say 1 to 1 equals to f of y 1 to 1, that means, because then I know it's 0, 0, it's a lot harder to do. I'm still talking about 9.
Oh, 9. Okay, sorry.
Like you said something about the b, how?
Oh, so if I know there's a critical point, let me make that more general then. If I know there's a critical point at AB, does this imply that fx of AB equals fy of AB equals 0? Does that imply that? No, the mistake you're making, if you think so, is that that's not the only place where critical points could come from. It could also come from when these are, one or the other is undefined in some way. That's even a little worse, but it's still undefined. You guys with me on that? So there are two ways to go from here to here. That's not the only one, so you can't say that that means that must have been true, because it could have been it was undefined at that point. Cool. And the same thing happened in 180. You had the exact same situation. Critical points came from either the derivative was 0 or it's undefined. So what about number 10? Sweet. And in fact, I pretty much talked about this already. And that's where you just take a step back from the math for a second and see what's real quick. If you know that those two are 0, and you know that fxx and fyy have opposite signs, then d must be less than 0, and that automatically means saddle point. So 10 is C. What? Sweet.
Wait a second.
Oh, yeah.
For this number 9, can we simplify it and look at the function x squared plus y squared without the square root? Because it's going to have the same like behavior or something?
You could only do that type of thing if you're trying to do like a minimum distance. You with me? You remember those problems? Minimum distance between this thing and this. You didn't have to use the square root in the distance formula because if you minimize the inside of a root, you minimize the whole function. But I'm not talking about the distance between things. I'm talking about this function itself. And if I lose that root, I lose the undefined part of it. That is a part of this.
But then we'll get the f of x 0, which we will, when we compare the second derivative test, we don't have the f of x if it is negative or positive. So isn't that catching the...
Oh, so if you try to do the next step, you can still do fxx.
Yeah, but if it is the point 0, 0, right? So the f of x will be 0. So we don't have positive or negative.
Well, the fx will be undefined, and the fxx will be undefined at 0. So there's nothing we can do with it. I really want you to be careful about when are you allowed to alter the function you're using. And as a student, you get, and I was the same way, you get really optimistic when you see them take the square root symbol away sometimes. And that's only in very specific situations where doing that doesn't alter the meaning of what's happening, right? In that case, if I minimize the interior of a square root, I minimize the whole thing, right? Whereas this one is different. It's not a distance formula. It's actually, I would lose information about where it's undefined then.
You can kind of get around that by visualizing the problem as a cone, so it has a point. And the point, when it comes to a point, it is no longer, you can't ask those questions.
Exactly, I like it. Cool. So, a balance of this, and I think you guys get this from early on, was this class is very much about concept, it's about visualization, and it's about can you do the math. Okay? Doing the math by itself often will make it a lot harder if you just step back and think, what's this thing look like? What makes sense about what's going on here? Or if you just try to look at the graph alone, that's not enough, because it's kind of weird to tell what the hell's going on. So you need kind of like all three of those things together to make this stuff easier to do, or sometimes possible. Okay, so any questions on that? 12A? I'm hoping for the most part, those problems in 12A should be kind of nice, because again, it feels a lot like what we did in 180. And now for us, 180 is like, oh man, I didn't know how good I had it back then, right? So anything that feels like 180 here should be like, oh yeah, give me more of that. You know, derivatives set it equal to 0. That's awesome stuff. We're used to that.
Well, next year we'll be thinking about about this stuff.
Exactly.
Yeah.
So a couple of classes down the road, you're like, oh, 281, that was so easy. Okay. Now my hope for today is to try to make it, actually I want to make it to a preview of 13.2. So I want to finish 12.9 and 13.1. 13.1 and 13.2 you guys are going to like. I can say that and not feel that I'm lying or speaking too much. It's you guys might have heard about these things coming up, double integrals. Integration is always a little worse than derivatives, but nothing is different necessarily. The limits get a little freaky in 13.2, but nothing overly difficult. So 13.1, especially 13.1, is like you can totally take this. 13.2 is a little bit more difficult, but they're basic stuff. You're not going to see a lot of freaky multiple U subs or something. We want to get to the heart of the concept of multivariables, not throw weird integrals at you and see if you remember the forms. But 12.9, I'm kind of excited about this. Let me see if this works. I've improved my explanation. Let's see what happens. So many guys, after I say this, you're going to be like, that was your improvement? But let's see what happens. Because 12.9 is a little weird. The math of 12.9 is beautiful. It's solving systems of equations. Food, right? No big deal. The concept of 12.9 is kind of freaky. But let me see if I can make it not freaky. Let's take a very simple example. Remember, the only one that I feel comfortable actually doing up here on the board was our little ghost dude, right?
Yep.
All right, here's our little ghost dude. Let me center him around the origin. I'll pretend like I'm trying to. Okay, that's not bad. So, where would and let's say this keeps going, right? Keep going. So I just drew the little trace there in the XY plane. What would my level curves look like? Give me some multi-parabolas. Level curves, yeah. Either circles or ellipses. Let's just say circles to make this simple, right? So we'll say this is circular, not elliptical. It actually is truly circular. So they would be like this for the top, right? And then it would be circles from there on out. And let me make a point right here. When I do this, am I graphing every single level curve that exists for this? No. Of course not. I'm being smart about it. I'm like, that would basically be just a freaking record then, right? Little picture of a record. Because I'd fill it all in. Normally we do, this might be z equal to 5, z equal to 4, 3, 2, 1. Is that cool? Like this would be 5 up.
Yeah.
Then 4, then 3, then 2. Okay.
Since they're all fairly similarly spaced, wouldn't that have to be a cone if your z's are all 1 increments?
Yeah, let's get past that. I'm trying, yeah, you're right. I should have spaced it out a little bit more to show that. And his point is, what should be true about the level curve? Since what happens as they move away,
They should get
the
closer
slopes should be increasing there, right? So the z's should be changing faster, so it should get closer spaced out here. Cool, I like it. So accepting that, that's the way it should be. We'll work with the way it looks. If I drew, let's just say, I can walk through this any way I want to, right? I could plug a point in and get its output. Cool?
Yep.
What points could I plug in? Any points in there, right? So I could walk this line here, this curve, and just look at all the outputs of that. How we doing so far? Okay, because that kind of thing happens a lot. So I just use some kind of equation or pattern of my inputs to see what the outputs are along that line. Cool? So if I'm walking a mountain, I might want to say what's the highest or lowest I got on my path. Well, I got to look at what path I actually took, and then see how high it was at those times. Okay, cool. So if I draw, let me do something a little different. doesn't really matter, but let's say I take a path, looks like a ellipse here. So it would be something like this. Oh, wow, we'll just make it like that. How are we doing so far? Doing okay? That purple line, can somebody tell me? Let's start off kind of nice. As I'm moving in this direction, what's happening to my height? I'm getting higher because I'm getting closer to the middle. It's the highest. As I move in this way, I'm getting higher because my z-scores are getting higher. And of course, if I turn this corner and move that way, I'm going higher again. Cool. So once I get past that middle point, I'm going lower, lower. Where would the maximum and minimums be?
Either in the middle or
I like it.
maximum in the middle.
So like right here should be a max, right?
Mm-hmm.
And why is that? Because on this side, my z's are getting smaller, and on this side, my z's are getting.
You're going minimum.
I like it. So we can even identify if it's a min or a max. So this one should be min for that purple line. You with me? That certainly isn't the minimum of this thing, because this thing doesn't really have a minimum. But for that path I'm taking, that is the minimum height. And where would like a maximum height be? Because I drew it really horribly. Yeah. It looks like I'm trying to be that. Now, here's the key. Here is the magic key. Let me see if I can get this. What must be true about the gradient at that point? Now, let me take a step back from there. If on this side I'm going down, and on this side I'm going up, if I'm going around this way, if on this side I'm decreasing, this side I'm increasing, right at that point, gradient's equal to 0. What should be true about, well, the derivative there is kind of equal to 0, you with me? What should be true about the gradient? And actually, what's true about the gradient here for the level curve? It should be orthogonal. So there, the gradient would be pointing up. With me? Cool. And this purple line, the gradient there has got to be in what direction? In fact, where would the tangent line be for this? Where would the tangent line be right there? Would it be like this? Because that's the same idea as Math 180, especially because I'm just talking about this xy plane. It would be like that. So where is the gradient pointing? Gradient must be how related to the tangent? Must be orthogonal, right? So yeah, in this case, it might be pointing in that direction. But what's true then about the gradient? And let me be a lot more specific. This, of course, is my f. Cool? This is my f of x1. Related to it anyway. Those are my level curves for that. The purple is what I'm going to call my g of xy. This is my constraint function. Okay. So what are we saying then about the two gradients? This gradient and this gradient. At, for example, this point.
Orthogonal to each other.
Same.
Careful, they're not orthogonal to each other. They could. In this case, it probably points down. But what's true about those two? Are they perpendicular? They must be parallel, right? And another way to talk about parallel with vectors here is they are scalar multiples of each other, right? So if it's pointing down, no big deal. It's just a negative scalar multiple. That's officially known as parallel. You with me? Cool. So that must mean, can I write this then?
No.
You're like, well, yes, you can, Jeff, but would it be true? So if I know that they are, I just gave you the answer, and actually I got this kind of backwards. I just gave you the answer, I know that they are parallel. That must mean one is a multiple. And we use this symbol here. Exactly, this is lambda. Okay. So at the heart of this is just that on that path, the location of the min or the max must be the place where the gradients are parallel, pointing in the same direction. Why? Because they both have the same idea. That's where things aren't changing anymore. So the gradient must be pointing orthogonal to them both in the same direction, because that's kind of like the same thing is happening on the black line as is on the purple line. Now, in the book, they go a step further. You really don't have to do this, but they go. They say the purple line, this g of x, y, is kind of like a, it's a level curve of a more general surface. So I can kind of get to the conclusion a little quicker if I go there. What's got to be true then about this level curve of this thing? Is that cool? Can you guys see? I can just make a cylinder out of this, just take this and repeat it, repeat it, repeat it. Then wouldn't this be a level curve of it? And what's got to be true at that point about the gradient? It's got to be orthogonal to the level curve. Are you guys with me? And there you go. So then you have these have to be scalar multiples of each other. They have to be parallel. It has to be orthogonal at that point. Both of them have to be orthogonal.
At an experiment or anywhere?
At a location of extreme. Cool. So how does this boil down then to nuts and bolts? That's the idea of it. Right? This is the idea. The actual work is kind of nice. Let's see where I go. Oh, yeah, I'll do this. Let's do a specific example problem. Then I'll try to show you the true proof. This wasn't a proof. This is kind of like a feeling out. It certainly makes sense. I'll show you the proof. Here. Fine.
That's only at critical points. Only true at critical points.
Exactly. Stream. Find a stream of 4. So, to make this process work, you have to identify correctly what is F and what is G. Yes, sir?
Didn't you say at the top, where you wrote min? I thought you said that was a max, because it's going down and it's coming up.
Well, if it's going down and then coming up, it's got to be a mid.
Okay, I thought I just heard.
That's okay. They're not always going to be this nice. This is obviously the F, because they said it's F, right? But the F is always going to be the function you're trying to maximize or minimize. The G is going to be the function that tells you what points you're allowed to use. I said those two things slowly, you probably noticed. So the F is the thing you're trying to maximize or minimize. The G function is going to be the constraint on your points you're allowed to use. Special. Kind of like that path that I took here. That's the only points I'm using for that problem, is that path I took. So this is my G. What's my G function going to be then? Let me see if you guys can see that. What's my G function?
X squared plus 4y squared minus 4.
I like it. Minus 4.
Ooh.
Coolness. Okay. So here's how this works. All we really have right now is this, and that's all we need. So how do I get the gradient of F?
F of x, F x, F y.
So, and actually, let me just cut right down to how I do this kind of problem. Right? Here's how I do this kind of problem. Because this is going to be this. In this case, we only have two variables there. And this is going to be lambda times gx, gy. So what does that really boil down to? Fx equals lambda gx. You with me? And Fy must equal lambda gy. How many unknowns do I have in those two equations?
3.
3. I don't know x, I don't know y, and I don't know lambda. How many equations? I've only got 2 freaking equations. So the last equation is always going to be that g of xy 1 equal to 0. Okay. That's how you create your system of equations that will get you to the answer. Now, full disclosure, the problems you're going to see in this section in the homework are relatively easier problems that you can actually do a multitude of ways. This Lagrange multiplier approach, or Lagrange, however you want to say it. Lagrange multiplier, if you wanted, you see this a lot in physics. This trumps any other method you want to use when you start getting more complicated functions in here. So resist the temptation, especially on a test or something, to do this other than Lagrange multiplier. If I ask you to do it that way, do it that way. So what's this equation going to look like here? What's fx? 4x equals lambda times, what's gx? 2x. So that's one equation. Fy, 2y equals lambda times 8y, right? You guys with me? This is fx and gx, fy and gy. And then the last one is just this function here.
That's just g of x.
Equal to 0. I like it. So whatever the constraint function they give you, just get it equal to 0. That tells you what g is. Yes, sir?
So now we can use this method for the boundary.
Exactly, that's the idea. So that last problem from the last section that had a boundary condition, you could use this process instead. For that particular problem, the 2 methods are about the same in length. But like I'm saying, it's sort of like the difference between doing I wanted to use this example, but not many of you guys have done much with matrices, right?
No.
Too bad. Because it's sort of like a 2x2 matrix. If any of you did that math to solve a system of equations, that took longer than just doing the stupid equations itself.
Yeah.
If you guys remember. But then 3x3 is sort of a tie, and the minute you get above 3x3, matrices win hands down, right? 4x4, 5x5, the matrix works much faster. If you have never done matrices for solving systems of equations, sorry, that's my best analogy at the moment. So this is sort of going to be about the same amount of work if you did it a different way. Now, be real careful about this. Can anybody tell me what we should do next with these things? Yeah, you can solve for x or solve for lambda. I would actually get it to one side and factor it, right? Trying to solve this equation. So, and it's got more than one variable in it. I could solve for one and plug it in the other one, but the best way to do this is to get answers for this one and then plug them into the other ones and see what happens. So if I pull this sucker over, yeah, I get 2x, 2 minus lambda equals 0, right? Is that cool? So then what are my answers for this? X could equal 0, or lambda could equal 2. How are we doing so far? Okay, cool. So then I take these. I take x equal to 0, for example, and I can plug it directly into here. If I plug x equal to, and of course I can't use this because this is nothing but y's there. But if I plug it into this guy, what do I get?
Y equals 1.
Yeah, I get y equals
1.
Plus or minus 1. Cool. Right? Y squared equals 1. Yeah, cool. With me? And if I plug lambda equals 2 into here, what do you get?
0.
Y equals 0. And then you plug y equals 0 into here. You get the idea? You take one of those equations. This is how most of these work. They don't all work this way. There's going to be a little bit of mathematical manipulation on your part. But this can get you through most of them. You take the first one you see, you solve it. You plug those answers you got into the other ones, because the whole idea of a system of equations is they all have to work at the same time. So if this one only works at 0 and 2, These other ones have to work there also, so go ahead and plug them in.
Did you plug lambda?
Did you get 3?
in?
Yes. Lambda equals 2 there, right? So then you get 2y equals 16y. Cool. You guys with me? And if I get y equal to 0, now I plug that into here. And if you plug y equal to 0 to there, what do you get?
X is equal to ±2.
Plus or minus 2. I like it. So how many critical points did we end up with here?
Many.
Many. What are they?
0, 1, 0,
Zero, I like it.
1.
We'll just consolidate them. Sweet.
Did you get your number, third equation again? Was it from the
Oh, here?
G or the here?
Or here?
No, yeah.
Here?
That's from the G, right?
That's for the G, exactly. That's going to be when they say along the ellipse, using points from this curve. That's your constraint. It tells you what points you're allowed to use. That's your G function. Yes. And your F is the function that represents what you're trying to maximize or minimize.
What did you plug to get x plus or minus 2 down there?
Y equals 0.
Into where?
And there's only one left.
Okay.
This would be redundant, right? So it's got to be this guy. Okay. Yes, sir.
Are you able to combine the 2 and 1 for the xy's, or you can't mix those together either?
No.
Oh, you gotta be careful. X equal to 0 goes with these.
Oh.
Yeah, y equal to 0 goes with these. You can't make a plus or minus 2 plus or minus 1. That's 2 points that don't work, or 4 points that don't work. Now the really nice thing about Lagrange multipliers, if you look on page 865, at the bottom they got kind of like a little box that shows you the steps. The steps aren't all that intense. But the really nice thing about this method is that it's exactly like absolute max and min. You just pick the largest and smallest values. So to find this out, I would look at f of 0. And why can I do this? What about the function tells me I can do this? Squared. Yeah, it's squared, so who cares? So what is f of 0 plus or minus 1? 2. 3. So you get 0, you get 1, squared is 1 plus 2 is 3. Cool. And what is f of plus or minus 2, 0?
10.
10, I like it. So these are the two absolute mins, and these are the two absolute maxes. Cool.
So for that path, right?
For that path, I like it, thank you. So this is the location and value of absolute max and min on this path.
So we can say this is for the whole function.
For the whole function, no. Because we only use a subset of the points. Cool. Okay, how are we doing so far?
The location and
Yes.
value.
Yes, the location and the value. Locations, value. This
Why did you not solve for lambda in the y equation? You solve for it in the x equation, does that mean that?
I didn't have to, and it's because what's the only value that works for lambda in the first equation?
Is 2?
And they have to, any answer you get must work in all of them.
Okay.
I really want you to get this. That's why I only had to solve the lambda here. Because the only lambda that works for this equation is 2. So if lambda equals 3 works here, who cares?
You should pick the one that's easier.
So let's see what we get. Number 2, real quick.
This would be 1/4.
See, 2y minus 8 lambda y equals 0, so you get 2y, 1 minus, you can do it, Jeff, 4 lambda. You get lambda equal to 1/4. Now watch what happens if you plug that into the first one. 4x equals 1/4 twice x. You still get x equal to 0, right? Do you follow? You with me? So it doesn't give you any new information.
Okay.
Okay.
You said, okay.
Because the first one tells me x must be 0, or if x isn't 0, lambda must be 2. So lambda wasn't 2, was it? We found lambda equal 1/4 in the other equation. So when I plug it in, what's it gotta come out with? X must be 0 for this to work. So you don't have to find all the lambdas. You solve one equation and then plug what you found into the other equations. Because of the fact that they all have to work at the same points. Do you see that? Sort of semi. Okay.
Does that have to do with when you were saying it was a scalar of that too? Scalar of the.
Yeah, so the interesting thing about this is at that location that leads to, the scalar multiple is 2. So the gradients are offset by a multiple of 2 at that location. I like that. To get the answer, that doesn't matter to explain what the hell that means, but that's what that means visually. One gradient is twice as long as the other. Okay, cool. Let's see. Oh, real quick. I want to show you, let's see if I did this. Oh, here we go, cool. Let me show you something. There is, with these problems, you can't exactly solve them the way we did that one problem about the boundary points. And I'll show you why. This problem here, and we have the constraint. Where'd it go? Let's just say it's this here. Let's just even not even use that. We'll just say it's got to come from there. You guys with me? Like that's the boundary that I'm using. You guys with me? Okay. The way we would have done this before would have been something like this. Right? Remember this? Because what's wrong with this equation? It's got too many variables in it. So let me solve that one. Then what do I get here?
2, 8 minus.
Yeah, I got 8 minus 8y squared plus y squared plus 2. Right? So I get f, this was f of x, y. Now I've effectively made it f of y. 10 minus 7y squared. So now it's a one variable. F prime equals negative 14y. If I set that equal to 0, I get y equals 0, which will lead to the same things we got before. But what about my other points? I will pick up my points plus or minus 2, 0, right? If that's what they were, I think.
Yes.
But I won't pick up the other ones, the 0 plus or minus 1.
Don't you do it the same thing for the other one?
I like it. So you have to do the whole process again, but instead of solving for x squared, solve for y squared. Actually, what I do is this. So when you rewrite this, this will be f of x now. It'll be 2x squared plus 4 minus x squared, or 4.
Are you just using the function that was originally given?
Exactly.
F?
Yeah, exactly.
So
Cool. Trying to reduce each one down to a single variable so I can attack it directly with 1/8. So do you guys see? If I only do it this way, I miss out on the other answers. Now we were lucky, and in fact you would be lucky in the problems that they gave us in the previous section because we didn't have that method to do it. But now you have to actually do it both ways to get all the answers. So that method over there is a little more direct. You don't have to go back to the beginning and start over again, right? This Lagrange multiplier just gives me the answers all of them directly. Okay, maybe. Okay, all right. So, and again, this equation tells me the points that I'm allowed to use. That's why it's a really good intuitive step to say, let me just plug the damn things in then. Solve for x squared, plug them in. I can only use those points. Well, let me use them. And then I get a nice one variable equation, attack it with 180. The problem is you don't get all the points unless you go back and turn it around. Solve for y in this case, and then keep going. You will pick up the other ones if you do that. Okay, so I'm going to give you guys one to try, and then I'll consider how much I'm going to show you with the proof. Try this one. This is page 869. Try out number 9. instructions are use Lagrange multipliers to find the max and min of this on this given boundary, on this given constraint. The very first step was solving for x squared. Because then I can plug it into the x squared that's in the equation, right, into the f. So if I plug that 4 minus 4y squared, I double it, that's where the 8 minus 8y squared. So I just took this here, and plugged it there. Cool. And why did I do that? Because that's what we do when we have more than one variable, but we have two equations. We use the one to plug into the other one to get down to one variable. The new twist here is you actually have to do it for each variable to be able to catch all their points. What do you guys get for the first equation here, the fx equal lambda gx?
Negative 8.
Negative 8. equals lambda 2x.
2x.
Cool. And this guy,
2y equals lambda 4.
4.
okay, cool. So this feels a lot like the one we just did. Right. And this first one, if I add that over and take out a 2x,
2x.
I get lambda plus
4.
4. So x equals
0.
0, or lambda equals
Negative 4.
negative 4. Like.
Wait. Did I do something wrong? I just made it negative 4 plus
So I just added this
oh,
over.
let's do this minus. Never mind.
Okay.
It's minus.
So again, in this equation, there's no x, so I can only use the lambda. If I plug in lambda equal negative 4 in there, that of course is going to lead me to what? Y equals 0. Because again, it just makes it a constant. So it's still going to be y equals 0. So this leads me to y equals 0, which leads me to what from this? X equals plus or minus 2.
Y equals
And then if I plug in x equal to 0, that leads me to,
y equals plus or minus square root 2.
I like it. So to finish this out, you just got to plug those points in, and those points are, and again, this not all of them. I got to be careful. I wanted to pick one that's sort of like what we just did, but this is almost exactly like what we just did. I want you to feel like it's always going to be like this. Notice how neither of these has the other variable in it. Is that always going to be true? No. All right, so it's a little too easy right now. How do I determine what's in max or min? Plug them in. So I can plug in like I did last time, because these are squared. I can plug in 0 plus or minus radical 2. And what do I get in either case?
2.
2.
Minus, plus minus.
2.
So if you plug in, yeah, so you get 2. And if you plug in plus or minus 2, 0.
Negative 16.
Negative 16, I like. So this is obviously the
Max.
max, absolute max,
Min.
absolute min. So you can answer the question, you can say, where is it? There. What is it? There. Right, that distinction. Where does it occur and what is the actual value?
Where do you have the 13?
Yeah, let's do one more that's a little bit more interesting. Oh, you would pick that one.
You don't like that one?
No, it's good. Just taking the next step to the next dimension.
Oh, yeah.
Probably the only place I could say that, not everybody think I'm crazy.
Let's take the step to the next one.
13 is, you think you're crazy anyway.
Oh, yeah.
Oh, yeah.
And does that same apply to the lambda, right?
Say again, sir?
So the lambda, you don't have to solve twice now?
Exactly.
Same.
Or in this case, with 3 variables, this would exceptionally suck if you wanted to try to attack it like the other way that we did the other problem earlier,
Oh,
the
yeah.
non-Lagrange multiplier. The minute I get any more variables in this, Lagrange multiplier beats it out. So let me see if you guys get the idea, if you can take it the next step.
So you just add on.
Exactly, yeah, you just add on one more line.
That's it.
So many variables that actually really just add here to worry about. One. So I really just have to add one more equation, which is going to be the natural next equation. FC equals lambda GZ. Now the minute you add more equations into a system of equations, you inherently make it a little more difficult than it would be with just 3. But it's not that bad. So what's my fx equal lambda gx? I'm gonna leave you 2. My gxy is going to be x, y, y, x, y, z. Minus 25. So that's going to be my 4th equation.